Konstantin Serebryany from Google. Thank you.
Thank you. And here is my team from Moscow. We develop, deploy, and maintain various testing tools at Google. And today I will talk about two bug detection tools, both of which are based on the LLVM. First, I will talk about AddressSanitizer, which is a memory error detector. Then I will mention ThreadSanitizer, second tool which finds data races. And I will also mention some challenges to all of us who develop compilers and testing tools. And please feel free to interrupt me at any time with questions. So let's start with the memory bugs that come with the beautiful language C++. We have all kinds of them, and this slide mentions only the most frequent bugs with memory. So first of all kinds of out-of-bound accesses to heap, stack, and globals, which are also called buffer overflows. You have all kinds of use after frees. You have use after free for heap, and you also have use after return for stack. You may also read some uninitialized memory and use it, trying to make some sense of it. There are also a lot of other more boring memory bugs, which I will not discuss anymore today. So please raise your hands if you know any tools that detects some subset of these bugs. Good. So name me one, please. Okay. Huh? Okay. So I've heard. Huh? Okay. Valgrind won the election. At least let me assume that. And let me compare the tool I will be presenting today with Valgrind, because Valgrind is indeed a state-of-the-art tool for finding memory bugs. So the tool, which is called AddressSanitizer, finds some of the bugs that Valgrind doesn't, namely bugs related to stack and globals, stack out of bounds, global out of bounds, and use after return. Unfortunately, it doesn't find uninitialized reads, which Valgrind does. So if you want to find all bugs, you still have to run Valgrind. A very nice feature of the tool, of our tool, is that it is very fast. We usually see less than 2x slowdown. Also, due to the complexity of the Valgrind implementation, it is available only on POSIX operating systems, Linux and Mac basically. AddressSanitizer is much simpler. It doesn't depend on the operating system, and it can be implemented everywhere where we have open source compiler. Actually, the closed source compiler vendors could implement it as well for their systems. Right now, still we only support Linux and Mac as well as Valgrind. Let me first give a brief overview of the tool. So it uses compile time instrumentation, and we currently rely on LLVM, and the compiler model is very small. It's just about 1,000 lines of code. We also have a GCC variant work in progress, basically implemented half of the functionality, but it already works. The second component is a runtime library. It's a bit more than I would like it to be. It's about 5,000 lines. The current version supports x86 all flavors on Linux and Mac, and ARM Linux port almost works for us. We shipped the first version of the tool to our users in May this year, and since that time the tool found many hundreds of bugs everywhere we applied it to. First of all, Chromium project. We found a lot of bugs in the Chromium code itself and in many different third-party libraries that Chromium depends on. First of all, WebKit, FFmpeg. We found a bunch of bugs in our server-side code, and surprisingly, even one bug in Clang itself. We hope to have all of the tools code in the LLVM mainline very soon, and half of the code is actually already there. How does this work? First, a simple observation. Let's take any 8 aligned bytes of your program memory. These bytes may only have 9 different states with regard to their addressability. The first k bytes are addressable, and the rest 8 minus k bytes are not addressable. They cannot be more than these 9 states for any aligned double word or Q word. This means that we can encode the state of any aligned 8 bytes in just 1 byte. And we call this byte shadow byte. Actually, we can go even to more extreme, saying that we encode the state of 128 application bytes in 1 byte. And this will also work. So if we want to check that a particular address of memory is addressable, we instrument the program either dynamically or statically, like shown on this slide. This represents the instrumentation for an 8-byte access. So we have the application address A. We compute the address of the shadow byte for this application address. We read this shadow byte, and if it is not 0, it means that we cannot use this memory, and we have to do whatever to report the bug. Instrumentation for smaller accesses is just slightly more complex. It adds like 3 arithmetic instructions and nothing else. The tricky part is how to compute the address of the shadow byte based on the application address. And this actually is also simple. All we do is we shift the address by 3, basically dividing it by 8, and add some magic offset constant. Why does it work? This mapping, application to shadow mapping, divides the address space into 5 pieces. The topmost and the first and the last pieces are accessible to the application, and these constitute 7/8 of all of the address space. So your application may do whatever it needs to be done there. And 1/8 of the address space is dedicated to shadow and the prohibited region. So when you map the application memory using this function, you end up in one of the shadow regions. And when you try to map the shadow region, you end up in the prohibited region, which means that if for some reason the application code tries to access the shadow memory, it will immediately trap. Does it sound simple to you? It actually can be even simpler because we can say that the magic constant is 0. And then we end up with just a single instruction that computes the shadow byte. Unfortunately, it doesn't work by default. You have to supply the -fpi compiler switch, which will make all the application addresses go up, and you will be able to map the section at the very bottom. But this is worth doing with AddressSanitizer because it adds about 6% speed up. The question which we didn't solve yet is whether we can leave it as the only default mode or we still have to use offsets for someone. This slide shows an example of x86-64 code generated by LLVM for a very simple function. The original function had just one store instruction, and the instrumented code It takes a register, shifts it by 3, adds the magic constant using 2 instructions because the constant is too big. Then it compares the result of the load from the shadow memory with 0, and if it is not 0, it jumps to the code that crashes. In this example, we have instruction that generates illegal instruction exception, and before that, we put the original memory address to some fixed register so that the signal handler knows where to find the address. Another way to do the same thing is just to call a runtime function. It's slightly slower, but works the same way. Besides instrumenting the memory access instructions, we want to do something with stack and globals so that we can say this stack is a good memory and that stack is a bad memory. The same for globals. So for stack, this is also called red zones. When you have an object and you have red zones around it which are not accessible. So for stack, there are 2 possible ways to insert red zones, or as we call it, poison the red zones. We can do it in a fast way, such that we only poison the red zones, and we assume that the actual local variables are always unpoisoned. This is fast. This requires the number of instructions proportional to the number of local variables in a function. But it's a little bit tricky to implement in the presence of exceptions and long jumps because you have to unpoison the red zones when you exit the function. And another minus is that with this protocol, there is a small chance of finding use after return bugs. So the second protocol is slower. It has to poison the entire stack frame, but it is more reliable in presence of exceptions, and it finds use after return with better probability. Let me try to explain it on a piece of code. So suppose we have a stack variable of some amount of bytes, and the code that uses it in some way. This would be the fast protocol for poisoning stack. So we insert a red zone before the stack object. Then and the red zone has to be 32-byte aligned. Then we insert the red zone at the end of the object, and the end of the red zone also has to be 32-byte aligned. We compute the shadow address of the first red zone, and then we poison the red zones. And when the function exits, we only have to unpoison the red zones. So as you can see, we have only 6 store instructions per this function. The slow protocol will require to poison the entire shadow. So here we have 300 plus bytes of the local variables, and we need 13 store instructions to poison the stack frame. And when we exit the function, we poison the entire stack frame, saying that this stack frame is dead, don't touch it. Instrumenting globals is pretty simple. When you have a global, instead of it, you create a structure which has the original type and then the red zone padding, which is 32 bytes plus alignment up to 32 bytes. The use after return bugs are tricky because the stack is reused very soon after it has been after it dies. So the default mode the tool uses will find use after return only occasionally, and these bugs will manifest like some very strange buffer overflows. We only have a special, slightly slower mode, which basically puts all these stack objects on a heap, on a specialized heap. And that makes use after return bugs detectable with very good probability. And the heap used here delays the reuse of the dead frames. So we can detect use after return quite long time after the return from the function. So that part was about the compiler model, and that's what 1,000 lines in LLVM does. The rest of the tool lives in the runtime library, which is larger but mostly simpler in the logic. It initializes the shadow memory at startup. You have to map the shadow region so that no one else maps it for you. It provides complete malloc replacement. It doesn't use libc malloc. And our malloc implementation does the usual things that other tools do. It inserts poison thread zones around the allocated memory. It delays the reuse of the freed memory. And it also collects stack traces for every malloc and free so that we can provide a useful error message to the users. We also have to provide interceptors for a number of libc functions because since we're doing a compiler instrumentation, we're not instrumenting libc functions, and effectively we're not finding bugs in them unless we provide our own versions that do error detection there. And the runtime library also does various bookkeeping to provide useful warning message. And this is how the warning message look like for the case of use after free. So it tells you the kind of the bug in the first line. It tells you the address, PC, stack pointer, whatever. It gives you whether it is a read or write, which size, which thread, and the stack trace. Then it gives you a position inside the allocated or deallocated region. This time it was inside 400 byte region. And it also gives the offset. And then it gives the stack trace. In this case, it gives you the stack trace where the memory was deallocated and also the stack trace where the memory was allocated before that. This is my favorite slide. A lot of colors. It shows how the tool behaves on the spec CPU 2006 benchmarks, which are the tests we actually don't care about. But still, they provide good information to present at a meeting like this because everyone knows what spec is, and we can sort of speak the same language. So the red bars correspond to the full instrumentation where you instrument reads and writes, and the blue bars represent the station where you instrument only writes. So you find a subset of bugs, most critical bugs, but much cheaper. The average, as you can see, is 1.73x slowdown, less than 2x, for full instrumentation, and about 25% with instrumenting only writes. I have a hypothesis that every program has twice as many reads as writes, and this data proves my hypothesis. So the peak slowdown appears on two benchmarks. We see 2.5x slowdown, but most of the benchmarks are much less than 2x. A little bit about benchmarks, or actually programs we do care about. Surprisingly, for many GUI applications, you may not observe any slowdown at all. because a typical GUI application, at least if you have a decent hardware, does not eat all of the CPU. So you raise up the CPU usage twice, but it's still not 100%. And let me try to prove it to you. As you can see, this presentation is made by is done in the Chrome browser. This is almost regular build of Chrome. It can open LLVM. It can open whatever else heavy page. But if you open some specially prepared file, which I won't show to you, something bad will happen. And if I go to the terminal window, I can show you that this is a use after free being detected. So the Chromium browser I'm using to make this presentation is built with AddressSanitizer. And you didn't observe any lags in scroll. I hope you didn't. Okay, so we just close this window, this, and we can continue the presentation. So for the GUI programs, you often don't have any slowdown unless you do something like 3D rendering or something CPU consuming. For the server-side applications, we have very different performance figures. And unfortunately, the larger, the slower. And we didn't yet figure out why this happens. I would suspect instruction cache problems, but I don't have data to prove it. For one of the largest applications we tried, we observed something like 4x when compiled with O2, and even more, up to 8x when we compile with O1. We prefer to compile with O1 because O1 produces better error messages because inlining is disabled. But 8x is a little bit too much for us. We cannot afford it. So 4x is somewhere at the boundary of what we can afford. For many of our use cases, slowdown is less of a problem compared to memory overhead. And the memory overhead is quite usual for this kind of tool. So you have all those red zones. Mostly the heap red zones add the most of the overhead. You also have the quarantine for the freed memory, which is actually fixed size pool, so it's a constant. And then you add all this application memory and add 1/8 of it because we have to store the shadow memory for all of this stuff. For the real applications we tried the tool on, the memory overhead usually ranges between 2x and 4x. But on corner cases, we've seen numbers from tiny to 20x overhead. The stack size increases. Usually, you won't see it. But if your code uses a lot of local stack arrays, then stack may increase substantially. We have seen up to 3x increase in stack size. The tricky thing about the tool is that it uses quite a bit of address space, especially on the 64-bit machines. So on 64-bit machines, the tool will map 16 terabytes of RAM. And as you see, this is a 64-bit box. It works. You don't need to have 16 terabytes of real memory to make the tool work. On 32-bit machines, it's quite small. It's half a gig. Any question about AddressSanitizer so far? Yes. It's the same. Yeah. How is the memory overhead compares to Valgrind? With the same red zones, it's the same overhead for heap. Valgrind doesn't handle stack and globals. But we, by default, we use larger red zones. So by default, we get more overhead than Valgrind. Okay, so I'll go to ThreadSanitizer. I will not talk as much about this second tool today. It's a dynamic detector of data races. It uses more or less state-of-the-art techniques to detect races. The algorithm was published 2 years ago, and there are a few more or less similar tools on the market, with the one exception that we can use ThreadSanitizer for our programs, and no other tool actually works, surprisingly. For Linux and Macintosh, it uses Valgrind as a binary translation framework. For Windows, it uses Pin. We're using it for almost 3 years at Google, and it found a lot of real bugs everywhere at Google, more than 1,000 at least. And the only major complaint of our users is speed. It's very slow. It's even slower than Memcheck. Usually, well, 30x slowdown is not unusual for heavy applications. So about a year ago, we finally decided to go from the dynamic instrumentation to static instrumentation, which is a little bit similar to what Microsoft and Sun did in their proprietary tools. And actually, the AddressSanitizer tool, which I just described, is a byproduct of our work on ThreadSanitizer instrumentation. I will try to describe the tool in just one slide. In very short, it is very similar to AddressSanitizer. You have a small compiler model, which does very simple instrumentation. It instruments every memory access by just inserting a call to runtime library function. It also has to instrument function calls and exits to keep the shadow call stack. And the rest of the race detection happens at runtime library. Currently, we have implementation based on both LLVM and GCC, and they're more or less similar. And they use the same race detection state machine, the same logic as currently used with the Valgrind tool. The runtime library also does a lot of interception for pthread, for malloc, and for other library functions. So the current status of the tool is that it can build and run pretty big applications such as Chrome, using both the GCC and LLVM variants. Initially, I wanted to talk more about the internals of the tool, but then I decided that the old algorithm has been published already 2 years ago, and we're in the process of redesigning it completely. So maybe in a year, I will be able to present a completely new thing, I hope. So enough about ThreadSanitizer. At the end of the talk, I want to mention a couple of what I think are major challenges for developers of tools like this. First huge challenge is the detection of uninitialized memory reads. So you can argue that, okay, Valgrind does it, Dr. Memory does it, Intel Parallel Inspector does it, everyone does it. But I would say that everyone who does it with 20x slowdown or worse. And this is not acceptable for many of our use cases. We want fast, we want 3x or something. And today we are stuck with the binary instrumentation because for uninitialized memory reads, we have to instrument the entire program. For bugs that AddressSanitizer detects or ThreadSanitizer detects, if you don't instrument something, you don't find bug in that function. That's all. For uninitialized memory reads, if you don't instrument something, you miss a memory store, and you start reporting false positives, which is bad. So the only idea we have currently is to use a hybrid tool that will do binary instrumentation like Valgrind does for libraries, and the rest will be done by the compiler. If you have better ideas, let me know, or just implement yourself, because I don't like this idea. This is horrible. And the second challenge is how to avoid the redundant checks these tools produce. This slide gives a few examples for AddressSanitizer, but the same idea applies to all similar tools. For example, if we have two memory accesses to the same address, which are not optimized by common sub-expression elimination compiler, we still don't want to check them twice, given some properties of the program, of course. And for example, if we have a loop that reads or writes an array consecutively, we actually need only the first and the last element to check for addressability. This will be much faster. Yet another example, consider we have a struct with two integers where the first one is aligned by 8. We access 2 of them, but we need only one check because we access actually 8 bytes. So these are very similar to traditional compiler optimizations, but the problem is that how do you test such optimization? If you optimize the generated code, you can test on all the code you have in the world. Because if you optimize it incorrectly, you will end up with the incorrect code and the test will fire. But if you optimize away some checks, you will only find it if you test it on incorrect program, and you don't really have many of them with good descriptions of what is incorrect. These are the two challenges which I ask everyone to think about, and we are also trying to figure out how to solve them. This ends my talk, and I will be happy to answer any question. Thank you. Yes.
So in your challenges slide, there were some of the optimizations like putting stuff out of loops, and the last case there we've got 2 values, and so you only need to check 1. So you're saying that the challenge is actually to verify that the optimization is performed correctly, right?
Yes.
Right. Some of these, the last one is safecode is something similar. It's very trivial optimization in certain cases. The other one is monotonic loop wasting. Safecode actually has it, but it actually has some bugs that we found, so we're currently working on that. So, okay.
Yeah, so AddressSanitizer, the question was, it was more a comment, right? That safecode does some of those optimizations. So with AddressSanitizer, the benefit of doing these optimizations won't be huge because the slowdown is already small. So we must be 101% sure that we don't lose any bug, and the correctness of this redundant check elimination should be absolutely bulletproof. Otherwise, I don't even want to think about it.
So one thing that might help is a fellow named Willender recently released a test suite for memory safety errors. That's something that can potentially help tools like AddressSanitizer and Safecode and others.
You mean a test suite that has programs that intentionally violate? That would be nice indeed. Yes.
I wonder, could you use something similar to what John Wagner used to generate incorrect programs, and use that to help verify optimization?
To some extent, yes. But yeah, you can generate a lot of weird code, but what programmers do in the wild is usually much more weird than you can generate. Yes?
Do you have a feel for the slowdown? How much is from the instrumentation execution and how much is from malloc being different?
The question was how much of the slowdown comes from the instrumentation and how much from the malloc. You see these two spikes on the Perl bench and Xalang. This is malloc. On these benchmarks, malloc adds like 60% or something. On the rest of the benchmarks, here in spec, malloc is almost not seen in the profile. However, on the heavy server-side applications that we use, malloc is the top in the profile. It contributes about 20% of performance because it's a heavy function. It poisons a lot of stuff. It goes through the linked lists. And which is even more frustrating, that 20% more is taken by stack unwinding. So we need to unwind stack on every malloc to provide useful reports. And they're never used because the program just runs. If it has bugs, it's a code red. We need to fix it. Yeah, so for continuous builds of those heaviest applications, we have to disable stack unwinding so that it runs faster. It will still find the same bugs. Yes, please. Say it again, please. So the question is, where do I insert this instrumentation? I insert the instrumentation at LLVM IR level. So the code already gets generated like this. It would be possible to insert instrumentation using binary translation. This is exactly what Valgrind, Dr. Memory, or dozen other tools does. I believe that compiler-made instrumentation provides better performance because you rely on the well-tested optimizer which goes after that, basically register allocator. In theory, it would be possible, I think, to have binary translation with the matching performance characteristics. Another thing that with compiler, you can easily poison the stack objects. And with the binary translation, I have no idea how to do it. Yes? Yes, that's the question from Intel. Why are we using pin on Windows and Valgrind on Linux and Mac? Pin is excellent. It has so many things that are better than in Valgrind. The only thing that is worse than in Valgrind is that pin is closed source. And it basically removes all the positive features of pin for us. If we had Valgrind for Windows, we wouldn't even touch pin. Because that's not a religious question. That's a very technological question. At our scale, no tool works out of the box. If we have bug in Valgrind, we fix it. It may appear in Valgrind trunk in half a year or never appear if they don't accept it. If we find a bug in pin, pin folks are very friendly, but we still have to wait a couple of months. Instrumentation itself, I would say in pin is slightly faster, but you also have to intercept functions. And that business is very messy, and in pin it is very painful, and the non-painful way is very slow. Basically, the non-painful way in pin requires to acquire a global log for every function call you intercept, which doesn't work.
Can you intercept remote procedure, remote function call? So create remote thread on Windows. Create remote thread is like from another process, you create a thread in another process.
Oh.
You don't know where the starting point of the function is, but the system will call the function. Therefore, you have no way of intercepting.
The question is about the threads that appear on Windows out of thin air in your process. Yes, those cost me a few gray hairs. Those are nightmare. Yes. question is, we intercept several libc functions. Whether do we plan to intercept more than libc? No. For the server-side applications, we don't really care about anything but libc because we don't have.
For example, something writes into socket. If it reads out of bounds, it's not a bug in the socket function. It's the bug in the feature, so you still need to catch it. So you need to know.
The question is about writing to socket, but writing to socket is a libc, right? It's just a wrapper to system call. We can handle it. So for AddressSanitizer, we have to intercept everything we don't compile. And on the server side, we compile everything but libc. We can actually compile libc as well, but it's a bit nasty.
So you compile every system library except libc.
What other system libraries would you expect us to use? Well, that too, yeah, but it's a minor thing. Hmm?
If you recompile everything, you can recompile.
Yeah, we actually can.
I guess it works for some cases.
We actually can.
Do you plan to provide more general solutions?
We'll see. I don't know. After 3 years using Valgrind, almost all of the bugs still appear in our own code. So we instrument it and we will find bugs there. But eventually we may want to have some solution that handles everything. Yes. Please. No, we don't handle inline assembly. That would require binary translation. It is possible with the hybrid tool, but we won't go there until we polish the tool and make all users, all C++ users at Google use our tool. Yes. Yeah.
Following up on the inline assembly code, could you do something like verifying that at least you're passing valid memory in and out of the inline assembly code using the UCC constraints?
Can we handle the inline assembly at least by intercepting the input parameters? Yes, we can. No, we don't do it. Thank you.